Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss packed towers versus tray towers. The very first continuous distillation column had 12 bubble cap trays with weirs, downcomers, tray decks, and bubble caps with internal risers. Current tray towers are quite similar. As most distillation towers have always been trayed rather than packed, one would have to conclude that tray towers must have some sort of inherent advantage over packed towers. And this is indeed true in a practical sense, even though, in theory, a packed tower has greater capacity and superior separation efficiency than a tray column. How packed towers work. The original packed towers used Raschig rings, hollow ceramic cylinders, typically 1-inch outer diameter, OD, 0.75-inch inner diameter, and 1-inch long. A state-of-the-art packing is called structured packing. This material is made of thin sheets of crimped or corrugated metal, with small holes, fastened together with thin bars. The metal selected for the sheets is typically 316 stainless steels. The two features that should be maximized in packed beds are open area, the average percentage of the cross-sectional area of the tower not blocked by the packing, and hence available for the flow of vapor and liquid. Wetted surface area, the number of square feet of packing surface area available for vapor-liquid contacting, per cubic foot of tower volume. The greater the open area of packing, the greater the capacity of a tower. The greater the wetted surface area of a packing, the greater the separation efficiency of the tower. For example, a packing consisting of empty space would have lots of capacity but awful separation efficiency. A packing consisting of a fine sand would have great separation efficiency but very low capacity. So, the selection of packing for a column is a compromise between maximizing open area and maximizing the wetted surface area. Structured packing has about 50% more open area than Raschig rings and 2 or 3 times their wetted surface area. Hence, structured packing has largely replaced packing in the form of rings in many packed towers. In any type of packed tower, the liquid or internal reflux drips through the packing and forms a thin film of liquid on the surface of the packing. Vapor percolates up through the packing and exchanges heat and molecules with the thin film of liquid on the surface of the packing. In a tray tower, vapor-liquid contact occurs only 5 or 6 inches above the tray deck, and the majority of the tower's volume is not used to exchange heat or mass between vapor and liquid. In a packed tower, the entire packed volume is used for this vapor-liquid contacting. In a tray tower, the area used for the downcomer that feeds the liquid to a tray and the area used for draining liquid from a tray are unavailable for vapor flow. In a packed tower, the entire cross-sectional area of the tower is available for vapor flow. This certainly makes it seem as if packing is vastly superior to trays, and even if this was not true in the past, with the advent of structured packings in the 1980s, it ought to be true now. But as a process design engineer, whenever possible I still specify trays rather than packing. Why? Liquid distribution. Each tray in a tower is inherently a vapor-liquid redistributor. The holes in the tray decks redistribute the vapor flowing up the tower. The outlet weir, or more exactly the crest height of the liquid overflowing the weir, forces the liquid to flow evenly across the tray. Even if the weir height is uneven on a tray, and liquid flow is distorted on that particular tray, the liquid will be properly redistributed on the tray below. Unfortunately, packing does not redistribute liquid or internal reflux. Unless the initial reflux distribution is good, the liquid flow distribution through the entire packed bed will be poor. This picture shows a common orifice plate liquid distributor. Vapor flows up through the large chimneys, and liquid drains through the smaller distribution holes in the tray deck. To calculate the height of liquid on this chimney tray, we have to add 2 factors. The pressure drop of the vapor flowing through the chimneys. The liquid on the tray has to develop enough liquid head to flow against the higher pressure below the tray. The orifice hole pressure drop. This is the liquid head, which has to be converted to velocity as the liquid flows through the orifice holes on the tray deck. The pressure drop of the vapor flowing through the chimneys is delta PV equals kCdV divided by dL times Vg square, where delta PV equals pressure drop of the vapor flowing through the chimneys and hats, in inches of clear liquid. Kc equals an orifice coefficient for a chimney plus a chimney hat, typically 0.6 to 0.9, dV equals density of vapor, dL equals density of liquid, Vg equals velocity of vapor passing up through the chimneys in feet per second. The orifice hole pressure drop is delta PL equals K0 VL square, where delta PL equals pressure drop of the liquid flowing through the orifice holes, in inches of clear liquid. K0 equals an orifice coefficient for a hole in metal plate, typically 0.4 to 0.6, VL equals velocity of liquid draining through the orifice holes, feet per second. The sum of delta PV plus delta PL is the total height of liquid on the chimney tray. Let us assume that this total height is 6 inches of liquid. Delta PV equals 5.1 inch. Delta PL equals 0.9 inch. Let's further assume that the orifice plate distributor is 1 inch out of level. This could easily happen in a 14 feet 0 inch internal diameter tower. This picture shows the results. The flow of internal reflux or liquid through the higher portion of the tray deck falls to 0. Worse yet, vapor starts to bubble up through any orifice hole that is not submerged by at least 5.1 inch of clear liquid. But, of course, once vapor bubbling begins, we do not have clear liquid in this region of the tray deck. Meanwhile, all the liquid flow must drain through the lower portion of the tray. The net result, as can be seen in picture, is dry packing in one portion of the tower and over-refluxing in the adjacent portion. This is called vapor-liquid channeling, and this is the root cause of poor fractionation efficiency in any tower. One way out of this problem is to increase DPL, the pressure drop of the liquid flowing through the orifice holes. This could be done by increasing the orifice hole liquid velocity. We could drill fewer orifice holes. Unfortunately, this would decrease the number of drip points per square foot of tower area. 6 to 10 is a good target. This would reduce vapor-liquid contacting efficiency. Or we could have smaller orifice holes. But too small a hole would probably plug with corrosion products. There are ways around these problems. This picture is a simplified sketch of a multi-pan liquid distributor using raised, slotted, guided drip tubes employing an initial distribution header. It is beyond the scope of this video to describe how this works. But I will say that such liquid distributors are expensive to build, tricky to design, especially for small liquid flows, difficult to install correctly, occupy quite a few feet of tower vertical height. Trade-off between efficiency and capacity. In a tray tower, we can increase tower capacity by reducing the number of trays and increasing the tray spacing. But reducing the number of trays in turn reduces separation efficiency. In a packed tower, we can increase tower capacity by using larger packing and increasing the open area or a bigger crimp size for structured packing. But the reduction in the wetted area of the packing will reduce separation efficiency. Installing a properly designed, efficient liquid distributor, such as the one shown in picture, will definitely enhance separation efficiency, but at the expense of the vertical height of the tower, which could otherwise be devoted to a greater height of packing. Vapor distribution. This picture shows a modern, narrow trough, liquid collector vapor distributor chimney tray. While the initial vapor distribution through a packed bed is not quite so critical or difficult as the liquid distribution, it is still important. A properly designed valve or sieve tray will act as a vapor redistributor. Thus, poor initial vapor distribution will only lessen the efficiency of the bottom tray. But if a packed bed vapor distributor does not work properly, vapor channeling will be promoted through the entire bed. The narrow trough vapor distributor shown in this picture is intended to disperse the vapor evenly across the bottom of the packed bed. The width of the chimney does not exceed 6 inches. The older style chimney trays, which may have had a few large round or square chimneys, reduced the separation efficiency of the packing. To work properly, the vapor distributor has to have a reasonable pressure drop in comparison to the pressure drop of the packed bed. For example, if the expected pressure drop of a 12-feet packed bed is 10 inches of liquid, the pressure drop of the vapor distributor ought to be about 3 to 4 inches of liquid. In practice, the most common reason why vapor flow is mal-distributed as it escapes from a well-designed chimney tray is distortion of the hats. I believe this is due mostly to workers stepping on the hats during unit turnarounds. The hat support brackets are designed to support a 20-pound hat, not a 200-pound welder. Maintaining functional and structural efficiency in packed towers. Pressure drop. A packed tower can successfully fractionate with a very small pressure drop, as compared to a tray. For a modern trade tower, to produce one single theoretical tray worth of separation that's like a single, 100% efficient tray, a pressure drop of about 6 inches of liquid is needed. A bed of structured packing can do the same job with 1 inch of liquid pressure drop, even when allowing for the vapor distributor. In low-pressure fractionators, especially vacuum towers used to make lubricating oils and waxes, this can be of critical importance. Packed beds also seem to have a better turn-down capability than valve or sieve trays at low vapor flows. On the other hand, many packed fractionators seem quite intolerant of reduced liquid or reflux flow rates. This is typically a sign of an improperly designed distributor in the packed fractionator. The problem we have just discussed, poor fractionation efficiency due to inadequate vapor and liquid initial distribution, is rather similar to tray deck dumping in trade fractionators. And, just like trays, packed towers are also subject to flooding. Flooding in packed towers. To understand what is meant by flooding in a bed of packing, one ought to first understand what is meant by the idea of holdup. Let's imagine we are operating the air water scrubber in the unit operations lab at university shown in figure. The water is circulating from the bottom to the top of the tower. The water level in the bottom is 2 feet. The height of the packed bed is 20 feet. At 3:30 p.m. Professor shuts off our air compressor and the water circulation pump. As the water, which had been held up on the packing by the flowing air, drains down, the water level in the bottom of the tower rises from 2 to 5 feet. We say, then, that the holdup of the packing was 15%, 5 feet minus 2 feet, divided by 20 feet equals 15%. If the liquid holdup is too low, fractionation efficiency will be bad. We say that the height equivalent to a theoretical plate, HETP, will be high. If the liquid holdup is too high, fractionation efficiency will also be poor. We again say that the HETP will be high. This idea is expressed in this picture. When the holdup rises above the point that corresponds to the minimum HETP, we can say that the packing is beginning to flood. The minimum HETP point in this picture corresponds to the point of an incipient flood, discussed in previous videos, for trade towers. For structured type packing, a liquid holdup of 4 to 5% corresponds to this optimum packing fractionation efficiency. For 1-inch Raschig rings, this optimum holdup would be roughly 10 to 12%. There is a close relationship between percent liquid holdup and pressure drop, as expressed in inches of liquid per foot of packing. If the pressure drop per foot of packing is 1.2 inch, then the liquid holdup is roughly 10%, 1.2 inch divided by 12 inch equals 10%. Unlike the perforated trade decks discussed in previous videos, there is no simple equation to predict the optimum pressure drop that would correspond to the minimum HETP for different types of packing. There is just too much diversity in both size and shape to generalize. Packed bed supports. A simple support for a bed of 1.5-inch Paul rings might consist of a bar grid with 0.25-inch thick bars set on 1-inch center. The grid itself in this picture would be supported by 2 6-inch wide I-beams. The open area of each component is 1.5-inch Paul rings, 80%. Grid support, 75%. I-beam support, 90%. Considering that the rings, the grid support, and the I-beam are all in close physical contact, what is the open area at their mutual interface? Answer is 80% times 75% times 90% equals 54%. This means that there will be a restriction to vapor and liquid flow at the grid support, which will promote flooding at the bottom of the bed. Naturally, this would cause the entire packed bed to flood. To avoid such flooding, the designer uses the corrugated bed support shown in this picture. This grid will have over 100% open area based on the tower cross-sectional area. Crushed packing lying on even this excellent type of bed support can, however, cause flooding if the crushed packing has lost most of its open area. Packing hold downs. During routine operations, the weight of a bed of packing is sufficient to keep it in place. But if there is a pressure surge during startup, the packed bed can be forcefully pushed against the underside of the liquid distributor. If this liquid distributor is a spray header, as illustrated in this picture, the spray bar arms can be bent. To prevent this, a packing top hold-down grid is required. This hold-down grid must be firmly attached to the vessel wall. For example, in a 12-feet ID tower, the hold-down grid is designed to resist an uplift force due to a pressure surge of 0.5 psi. What is the total uplift force? Answer is 0.5 psi times 144 square inches divided by square feet times 3.14 divided by 4 times 12 square equals 8,000 pounds. This picture illustrates a problem introduced when a packing hold-down was installed at the wrong elevation. This tower was designed to purify acetic acid by distilling overhead the lighter formic acid. But at even 50% of the design reboiler duty, the tower flooded, and acetic acid was carried over into the formic acid. The problem was that the perforated plate hold-down used to keep the 1.5-inch Teflon rings from floating up through the feed chimney tray distributor was located immediately below these chimneys. What, then, was the open area at the interface of the chimney feed distributor, the 1.5-inch rings, and the hold-down plate? Open area of chimney feed distributor equals 40%. Open area of rings equals 70%. Open area of hold-down plate equals 30%. Answer is 40% times 70% times 30% equals 8.4%. As a result, the tower flooded above the hold-down plate. To fix this problem, the packing hold-down was dropped 15 inches below the chimney tray. As a result, the tower fractionated properly. Incidentally, this incident was a multi-million-dollar mistake. It was not, however, a design error. The installation crew had simply found a cheaper location to install the hold-down grid by using the same support as the chimney feed distributor. Crushed packing. One of the great disadvantages of packing is the inability to properly inspect the installation. In one gasification plant, the off-gas scrubber flooded because of a plastic bag left inside a packed bed of Paul rings. On another tower, flooding of a bed of structured packing occurred at 50% of design. Only when the packing was removed for inspection was the problem revealed. Workers had previously stepped on and crushed intermediate layers of packing. Then, probably without realizing that they had reduced the open area of the structured packing by 50%, they set additional layers of structured packing on top of the damaged layers. The situation on a trade tower is far more controllable. Even after the tray assembly is complete, the process engineer, using only a crescent wrench, can open a few tray deck manways and double-check the tower internals. But to pull 6 feet of packing out of a tower is a major undertaking. Also, trays can be stepped on without damage. Beam supports and 40-pound air guns can be dragged across a sieve tray with impunity. Packings, rings or structured, require special handling during installation or turnarounds. To be frank, all packing installations that I have seen have been damaged to some extent. To summarize, the chief disadvantages of packed towers, as compared to trays, are difficulty of achieving proper initial liquid distribution, especially at small liquid flow rates. The need for a proper vapor distributor to achieve proper initial vapor distribution. Possible restrictions to vapor flow from the packing grid support or hold down. Problems in inspecting the final installation. Advantages of packing versus trays. Often, we remove heat from a tower at an intermediate point by use of a pump around or circulating reflux. This picture is a sketch of such a pump around. In many towers, the liquid flows in the pump around section are greater than in the other sections, which are used for fractionation. That is why we are often short of capacity and initiate flooding in the pump around or heat removal section of a column. Since we do not rely on pump arounds to fractionate but just to remove heat, good vapor-liquid distribution is not critical. A bed of 4 or 5 feet of structured packing is often, then, an excellent selection for the pump around section of a tower. The capacity of such a bed potentially has a 30 to 40% advantage over trays. Once a tower's diameter is 3 feet or less, trays become difficult to install due to the confined working area. Also, the tray support ring appreciably cuts down on the tower's cross-sectional area. Dump-type packings rings, saddles, broken beer bottles do not present such problems. Also, for high liquid flows in a smaller diameter tower, less than 5 feet, a well-designed packed tower will have a very substantial capacity advantage over a tray tower. In general, the lower the pressure of a tower, the greater the advantage of using packing over trays. Finally, the pressure drop of the vapor flowing through a packed tower will be an order of magnitude less than through a tray tower. For vacuum distillation service, this is often of critical importance. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.